rock. That sound, that's a sonic boom. It's loud, it's powerful, and it's the reason you haven't flown on a supersonic passenger jet in over 20 years. However, NASA has been quietly working on a revolutionary aircraft that won't boom, but thump. Just enough to hear it, but not enough to rattle your windows. Today, we'll explore the phenomenon of the sonic boom, the physics behind it, how iconic jets like the Bell X-1, the SR-71 Blackbird and Concorde made history, and how NASA's X-59 could shape the future. So strap in, as we journey faster than the speed of sound. So, let's start with the basics, and what exactly is a sonic boom? Anytime any object goes faster than the speed of sound, it starts to generate shock waves around that object, whether it's an airplane, whether it's a bullet out of a gun, anything going faster than the speed of sound is going to create shock waves. When those shock waves travel to the ground, that's what our ears perceive as a sonic boom. So, in simple terms, it's a shock wave in air, a powerful sound wave, created when an object moves faster than sound itself. To understand that, let's start with the speed of sound. Sound isn't instantaneous. It's basically pressure waves traveling through air. At sea level on a mild day, around 20 degrees C or 68 degrees F, sound moves at roughly 767 miles per hour, about 1,235 kilometers per hour. We call this Mach 1. An aircraft flying at Mach 1 is flying at the speed of sound. At Mach 2, it's going twice the speed of sound, and so on. Now, imagine an airplane flying through the sky. Even at subsonic speeds, slower than sound, the plane's movement pushes on the air in front of it, creating pressure waves. Basically sound waves that ripple outward. Normally those pressure waves spread out ahead of the plane. But as the plane goes faster and faster, these waves bunch up. The plane is trying to shove air molecules aside faster than they can move out of the way. Eventually, when the plane reaches Mach 1, all those pressure waves merge into one strong shock wave that form at the nose of the plane. At that critical moment, we are breaking the sound barrier. The air can't get out of the way quickly enough, and a sudden change in pressure occurs. This is the birth of a sonic boom. However, a common misconception is that a sonic boom is a one-time bang right when you break the sound barrier. When an airplane does that, it doesn't just make shock waves one instantaneous time. It makes the shock waves as long as it's flying faster than the speed of sound. Therefore, a sonic boom that is created by an airplane travels with that airplane. So it's a common misconception that once an airplane breaks the speed of sound and breaks the sound barrier, you get a sonic boom and that's it. But that's not the case. As the airplane travels, it drags that sonic boom with it, and we call that a sonic boom carpet. Everywhere that sonic boom touches the ground as the airplane flies. You can picture it like the wake of a boat spreading out behind in a V-shape. It's a 3D cone of pressurized air trailing behind, widening as it goes downward to the ground. Only observers inside that cone will hear the boom. If the cone doesn't touch you, you won't hear a thing. That's why someone on the ground hears a sudden boom after the plane has already flown past overhead. The plane is long gone, but the shockwave cone sweeps by you, and boom. It's like getting hit by a brief blast of sound energy. What does that blast actually sound like? Typically, a sonic boom is heard as a sharp double bang or a single loud boom. Why a double bang? Because usually two main shock waves form, one at the aircraft's nose and one at its tail. For a smaller aircraft or one flying very high, those two booms blur into one big boom that just sounds like an explosion or thunderclap. But for a larger vehicle like the space shuttle, people often distinctly heard two booms in quick succession. Boom, boom, as the nose shock and tail shock arrived separated by a fraction of a second. In either case, it's the sudden pressure change, essentially a pressure jump then drop, hitting your eardrums that make it such a jarring sound. Interestingly, the total change in air pressure in a sonic boom isn't huge, often on the order of only a few pounds per square foot above normal. That kind of pressure change is about what you'd feel riding an elevator down a few floors. The reason it sounds so loud is the rapidity of that change, a near instant bang rather than a gentle up-down in pressure.
This shockwave trailing behind the aircraft forms an N-wave pattern, named because if you graph the air pressure, it looks like a stretched out letter N. The pressure rises sharply, then declines and goes slightly below normal, then suddenly jumps back to normal. This pattern is why there can be two distinct booms, one when the pressure first jumps up, and another when it jumps back up at the end of the N-wave. Now, how far does this sonic boom carpet reach? Everyone under this moving carpet will hear the boom as the plane passes. The width of the boom carpet depends mainly on the plane's altitude. As a rule of thumb, it spreads roughly 1 mile in width for each 1,000 feet of altitude. So, a jet flying supersonic at 50,000 feet could produce a boom carpet about 50 miles wide on the ground beneath it. Directly under the flight path, the boom is loudest, and it gets weaker towards the edges of that carpet. If you're right under a supersonic jet, you'll get the full boom effect, whereas someone a bit farther off to the side might hear a distant rumble or maybe nothing at all if they're outside the cone. Let's break down the physics just a bit more without getting too dry. Remember how the shockwave forms a cone behind the plane? The faster the plane, the skinnier, more pointed that cone is. At just over Mach 1, the cone is fairly wide. At Mach 2 or 3, it narrows significantly. The angle of this Mach cone is determined by the ratio of the speed of sound to the speed of the object. In fact, there's a simple relation. Sine equals v sound over v object. Don't worry about the formula. What it means is that if you go faster, the angle sine gets smaller. For example, at Mach 1.4, the cone angle might be around 45 degrees. At Mach 3, it could be around 20 degrees. This is why supersonic planes often outrun the sound they make. The sound waves are confined to that narrow cone chasing the plane, not radiating all around. Observers on the ground hear nothing at all until the moment the shockwave sweeps over them. 1 second it's quiet, next second, boom. The plane is already far ahead because the sound was literally left behind and just caught up to you. But how do we get to creating sonic booms? To understand that, we need to travel back to the late 1940s. Pilots and engineers were itching to find out if we could push an aircraft past Mach 1. Back then, some people even wondered if a plane might be torn apart by the turbulence and forces at the sound barrier. Early high-speed dives in World War II aircraft had seen controls freeze up or wings flutter near Mach 1, feeding the idea of a destructive barrier. It took a special aircraft and a brave pilot to finally go supersonic in controlled flight. Enter the Bell X-1. This was a rocket-powered bullet with wings, built specifically to break the sound barrier. On October 14, 1947, over the Mojave Desert in California, Captain Chuck Yeager flew the orange Bell X-1, nicknamed Glamorous Glennis, and became the first human to officially fly faster than sound. Yeager's X-1 was dropped from a B-29 mothership, ignited its rockets, and zoom! It reached about Mach 1.06, 700 miles per hour at 43,000 feet. People on the ground heard the first man-made sonic boom from an aircraft in level flight as Yeager cracked through the Mach 1 barrier. That achievement opened the floodgates. Once it was proven possible, engineers rapidly moved to design faster jets. By the 1950s, jet fighters like the F-100 Super Sabre were routinely breaking Mach 1 in level flight. The Bell X-1 showed that with the right design, a streamlined shape like a bullet, very thin wings and powerful engines, supersonic flight was achievable. In fact, the X-1's design and the British experiments with the Miles M52 revealed one key solution for control. It had an all-moving tailplane, a stabilator, because a hinged elevator can lose effectiveness near Mach 1. This innovation of a moving tail would become standard on later supersonic aircraft. So, flying faster than sound isn't just about brute engine power, though that's certainly important. It turns out aerodynamics and materials had to evolve drastically to make supersonic flight practical. Let's talk about some of the key challenges engineers face when designing a supersonic aircraft. The aircraft's shape must handle the formation of shockwaves without losing control or creating too much drag. Early jets learned the hard way that thick wings and
blunt noses won't cut it. Supersonic planes use thin, swept wings or delta wings and slender, pointed fuselages to slice through the air. A concept called the area rule was discovered in the 1950s to minimize drag at transonic speeds, around Mach 1. The cross-sectional area of the plane should change smoothly, leading to that distinctive wasp waist or Coke bottle shape on some supersonic jets. The goal is to avoid sudden pressure buildups that make huge drag. Essentially, you design the plane so it disturbs the air as gently as possible, even when going supersonic. Going supersonic needs power. The Bell X-1 used a rocket engine because early jet engines weren't powerful enough. By the 1950s and 60s, we had afterburning turbojets that could push fighters past Mach 1. But an engine itself has a problem. Turbojet engines can't inhale supersonic air. The airflow must be slowed down before reaching the compressor blades. This is handled by clever inlet designs. For example, the Concorde and many fighters have variable geometry inlets, moving cones or ramps that create shock waves in just the right way to slow the air from, say, Mach 2 to subsonic speed by the time it hits the engine, all while avoiding instabilities. The SR-71 Blackbird had prominent shock cone spikes in its engine intakes that automatically moved to regulate the air and tame the supersonic blast of air entering the engines, allowing it to cruise at Mach 3+ without choking the engine. If you stick your hand out of the car window at high speed, it gets warm from air friction. Imagine that at 1,500 miles per hour. Air friction and compression at supersonic speeds generate tremendous heat on the aircraft's skin. The faster you go, the hotter. Concorde, which cruised at about Mach 2.0, would see its nose and leading edges heat up to around 127 degrees C, 261 degrees F. It actually grew by almost a foot in length during flight from the thermal expansion of its aluminium skin. The SR-71 flying at Mach 3 got even hotter. Part of its titanium skin reached over 300 degrees C, 572 degrees F or more in flight. Aluminium would weaken and melt at those temperatures, which is why the Blackbird was built primarily from titanium and had to leak fuel on the ground. The metal panels didn't fit tightly until heated and expanded in flight. High-speed aircraft often require special alloys, thermal protection, and careful engineering to deal with this heat. Even the paint matters. Concorde was painted white to reflect heat. One time, Air France painted a Concorde in a blue Pepsi livery for a promotion, but they were advised to keep it at Mach 2 for no more than 20 minutes at a time, because the darker paints could cause extra heating. Flying faster than sound means dealing with higher aerodynamic pressures and stresses, especially during maneuvers. The aircraft structure needs to be very strong, but also lightweight. This often means using advanced materials, titanium, high-strength steel, composites in modern designs, and careful engineering. It also means you often fly high, 50,000 to 60,000 feet for Concorde, up to 80,000 feet for SR-71, to find thinner air and reduce drag and stress. Early on, little could be done about the loudness of the boom except flying higher, which helps since the wave weakens over distance. For example, an aircraft at 50,000 feet will produce a softer boom on the ground than at 30,000 feet because the shock wave spreads out more and loses intensity over the extra distance. Engineers also learned that a long, slender airplane produces a weaker boom than a short, stubby one. This is partly why supersonic aircraft tend to be needle-nosed and slim. By spreading out the change in pressure over a longer vehicle, the shock waves don't merge into as strong an end wave. In technical terms, a higher length-to-width ratio can reduce the peak overpressure of the boom. This concept is at the heart of modern, low-boom supersonic designs. All these challenges mean designing a supersonic aircraft is a balancing act. You need a shape that's sleek for supersonic flow, but still safe and stable at lower speeds for takeoff and landing. You need powerful engines, but also ways to mitigate heat and drag. And of course, early designs were done with slide rules and wind tunnels, no fancy computers yet, which makes achievements like the X-1 and later the Concorde and SR-71 Blackbird all the more impressive. Concorde was the most famous supersonic airliner ever. In fact, the only successful commercial supersonic passenger plane to see service to date.